All right, let's jump right into this. Whenever we hear about the incredible feats of modern AI, whether it's writing code, diagnosing diseases, or even driving cars, we constantly hear the term neural network thrown around. But for a lot of us, what actually goes on inside that system just feels like pure magic. Well, today we are going to change that. In this explainer, we're going to completely pull back the curtain and decode the so-called black box, using some absolutely brilliant visual concepts straight from the famous TensorFlow neural network playground.
So the fundamental question we have to start with is, what exactly is a neural network doing inside that black box? Imagine just peeling back the layers of a modern artificial intelligence. We're looking right past the polished user interface to see the raw, internal mechanics at work. Now, I know it sounds incredibly complicated, right? But I promise, once you grasp the basic visual language of how data moves, it actually becomes this fascinating, logical flow of information.
Just to ground ourselves for a second, consider how the creators of the TensorFlow neural network playground define it. They say it's a technique for building a computer program that learns from data. It is based very loosely on how we think the human brain works. So essentially, you can think of this entire concept as a vast collection of software neurons sending messages back and forth to one another. It's really not magic at all. It's just a highly structured communication network.
Okay, moving on to part 1, what are hidden layers? If you picture a neural network as a factory, the hidden layers are literally the factory floor. They are these layers of artificial neurons situated right between your initial input data and the final output prediction. And this is exactly where the complex patterns are learned. Now, they're called hidden simply because they don't directly interact with the outside world. They don't see the raw data themselves, and they definitely don't hand you the final answer. Instead, they act as the core engine of the network, transforming those raw inputs into meaningful insights step by step.
Breaking down this anatomy gives us 3 very clear stages. First up is the input layer, which is where your raw data enters the system. Next, we hit those hidden layers we just talked about, where artificial neurons process and transform the signals. And finally, the output layer, where the network generates a final prediction. Understanding this anatomy gives us a really clear picture of what we call the forward pass. Basically, data flows strictly in one direction here, from the input straight through the hidden layers and out to the prediction.
Let's move to part 2, mixing outputs with weights.
So, we know these layers exist, but how do these software neurons actually talk to each other? Well, the answer lies in something called weights. Weights are numerical values that determine the importance or the influence of each input feature on the final output. Think of them as the physical connections between neurons that act kind of like a volume dial. If a piece of information is absolutely crucial for making a correct prediction, the network turns the weight or the volume dial way up. If the information is irrelevant, it just turns the volume down.
If we follow the journey of a single signal, we can actually map out this forward pass step by step. Step 1, data enters the input layer. Step 2, those outputs are mixed with varying weights, so that volume dial gets adjusted. And step 3, the neurons apply what's called an activation function. This function basically decides whether the neuron should fire and pass the signal along to the next layer. It's this continuous, rapid-fire chain reaction of data entering, getting scaled by weights, and triggering the next neuron.
Now, obviously, trying to look at millions of numbers in a giant spreadsheet to understand those weights would be an absolute nightmare. But in the neural network playground, this is brilliantly illustrated visually. Line thickness equals weight strength. So when you're looking at a visual representation of a neural network, a thicker connection line literally just means a stronger weight. An incredibly thin, almost invisible line, that means a very weak weight. It's a beautifully simple way to instantly see exactly which neurons are listening closely to one another.
All right, part 3, decoding blue and orange.
Okay, so we've got the line thickness down, but to truly crack the visual code of this black box, we have to understand the distinct color scheme they use. The crucial thing here is understanding what these 2 colors actually represent. Blue represents positive values and positive weights. Orange, on the other hand, represents negative values and negative weights. This direct contrast cements a fundamental rule of how the network operates. Blue means the network is using the neuron's output as given. It's like a positive reinforcement. Orange means the network is assigning a negative weight, essentially flipping or subtracting that influence.
Putting it all together gives us this incredibly helpful visual rule map. A thick blue line, that's a strong positive weight. A thin blue line is a weak positive weight. A thick orange line is a strong negative weight. And a thin orange line is a weak negative weight.
By literally just looking at the colors and the thickness of the lines connecting these hidden layers, you can understand the exact mathematical influence of one neuron on another, entirely without needing to read a single complex equation. You are literally seeing the AI think in real time.
Now, just to round out our understanding of the mechanics here, there is one more key ingredient added to this weighted mix, and that's bias. A bias shifts the output independently of the inputs. It essentially allows neurons to activate even if the incoming data signals happen to be very low. Think of it kind of like a baseline starting point. By adjusting the activation function for greater flexibility, bias is what helps the model fit the data far more accurately than if it relied on just weights alone.
And that brings us to part 4, the final prediction. So we've tracked the data through the input, watched it get scaled by those blue and orange weights in the hidden layers, and seen it adjusted by bias. Now we reach the absolute climax of the network's job. Millions of tiny, colored, weighted signals all combining in the output layer to form a single, confident prediction. All of those varying thickness blue and orange lines we just decoded pool together in that final layer to answer whatever specific problem the network was initially given.
When you're looking at the output layer in these visualizations, there's a very specific way to read it. The data dots themselves are colored orange or blue based on their original true values. But notice the background color. That actually reveals exactly what the network is predicting for a particular area. And the intensity of that background color? That shows the network's confidence. A deep, intense, dark blue background means the network is highly confident in a positive prediction. A pale, washed-out orange? Well, it's predicting negative, but it definitely isn't very sure about it.
But wait, what happens if that final prediction is just dead wrong? Well, that brings us to how the network actually learns over time. As the creators note, the network is asked to solve a problem, each time strengthening the connections that lead to success and diminishing those that lead to failure. This happens through an amazing process called backpropagation. The system learns iteratively. It looks at the errors in its final prediction, sends a signal backwards through the entire network, and adjusts the thickness of those blue and orange lines. It's basically turning those volume dials up or down automatically so that the next time it sees similar data, it makes a much better prediction.
Which brings me to a question I want to leave you all with today. How does understanding these simple blue and orange lines change the way you view the complex AI systems transforming our world today? When you realize that the most advanced neural networks out there are fundamentally built on these basic, microscopic interactions of color, thickness, weights, and biases, it really strips away the magic, doesn't it? And it replaces it with an immense appreciation for the architecture. It leaves you to ponder how these incredibly simple rules scale up by the billions to power the seemingly magical AI revolution we're living through. Thanks so much for joining me on this explainer, and definitely keep questioning what's inside the black box.